Welcome to NPTEL lecture, a basic course on electric and magnetic circuits. In this lecture, we will discuss on self and mutual inductances and then go to the dot convention in that scenario. So, let us consider a coil here as shown with the green mark here, having n number of turns, and this coil is energized with a current source I t. So, we know that the corresponding flux linkage through this arrangement, the coil which produces a magnetic flux phi in that electromagnetic circuit becomes n phi, which we call flux linkage lambda equals to n phi. The induced voltage across the coil becomes equals to d lambda upon dt. So, that gives us n d phi by dt. So, the voltage V equals to n d phi by d I into d I by dt, and this voltage we mark as V equals to L d I by dt. So, this L here is defined as L equals to n d phi by I, rate of change of flux with respect to I. So, this L here is called the self inductance of the coil in that circuit, and relates the voltage induced in the coil by the time varying current in the coil, by the current which is passing through the coil, that matters to the self inductance of the coil. L equals to n into d phi by d I. If you go by this, then the self inductance of the any electromagnet can be seen as like this. So, if you have this average inductance when the corresponding current goes from 0 to I and the corresponding flux goes from 0 to phi. So, the average inductance for that case lambda equals to n phi flux linkage, L becomes equals to lambda upon I, because n d phi by d I. So, n phi is a lambda. So, lambda upon I in this scenario. So, that becomes equals to L equals to n phi by I, and phi equals to B into A, and B equals to mu into H. So, by expanding this, if we see here, we get this to be n mu H A upon H L by n, where I equals to we know that n into I equals to H L. So, from there we can find I equals to H L by n, and that leads to the scenario of L equals to the self inductance of the coil equals to n square upon L by mu A. But this L by mu A is again S, the reluctance of the magnetic path, which we are already aware of. So, this L becomes equals to n square upon S, where n is the number of turns of the coil and S is the reluctance of the magnetic path. So, for such an electromagnetic arrangement, if you model, then the corresponding inductance of that electromagnetic circuit, that becomes equals to like this, where L becomes equals to n square by S. Now, note that this S is L upon mu A. So, S is L upon mu A, but we know that the mu value equals to mu naught into mu r, and the mu r comes from the B H curve. So, mu r in different regions, like if we say B H curve or B H loop. So, whichever you consider for your analysis. So, different regions will have different mu r value. So, therefore, the corresponding S value changes and the corresponding inductance value also changes in the different operating regions of the magnetic circuit. Now, let us take an example of this circuit where we have an magnetic core and an air gap. So, the magnetic core of the mean length is 50 centimeter, cross sectional area is 15 centimeter square, has a coil of 400 turns. The core material has a relative permeability of 3000, mu r is 3000. There is an air gap of 1 millimeter as shown. Obtain the inductance of the arrangement. So, this arrangement needs to be we need to find the corresponding equivalent inductance of this arrangement. So, L equals to n square by S. So, for this case the S equals to as you know S the core part plus the S the gap part, and each one is having L upon mu A. So, you can find it like this. So, dimensions are given L C, L G, A C and the mu r value. So, the core part S C becomes equals to L C upon mu naught mu r A C, and that comes out to be 88.42 10 to the 3 ampere turn per Weber, and the air gap part having the reluctance happens to be 530.51 into 10 to the 3 ampere turn per Weber. So, the L becomes equals to n square upon S C plus S G, where n equals to here 400. So, this gives out to be the corresponding inductance of the arrangement 258.5 millionary. So, we see that for such an electromagnetic arrangement with a coil, the corresponding inductance is proportional to number of turns square and inversely proportional to the reluctance of the path. Now, the next point is the energy stored in any inductor or the coil arrangement or electromagnet. So, let us see the corresponding inductance of the arrangement, equivalent inductance of the arrangement is L. So, we know d lambda by dt equals to induced EMF in this arrangement, where lambda equals to n phi flux in the magnetic path. So, E equals to again we know L di by dt, as already you have seen. So, we see here the voltage across induced voltage across this point E happens to be E this, and the current which is entering to this circuit is I. So, the power becomes E into I. So, that E into I the power, and at a time dt the corresponding energy associated. So, E into I into E into dt the energy. So, that becomes equals to L I into d I joules. So, the total energy absorbed in a period where the current rises from 0 to capital I. So, integrate this part from 0 to I in a time of 0 to t. So, that becomes equals to L I into d I integration by I to d I from 0 to I. So, that gives us the value to be half L I square. It means that the energy is stored during the process when the current rises from 0 to capital I. The energy is stored in that mechanism, that setup, that electromagnetic mechanism happens to be half L I square joules, where I is the current in ampere and L in Henry. Furthermore, we know that the L we have defined n square by S. So, that becomes equals to half I n square mu A upon A L, and that equals to half H L square upon mu A by L. So, we can say that N I equals to H L. So, that becomes equals to half mu H square into V C, where V C is the volume of the core, cross section area A C into the length of the mean path. So, that becomes equals to A C. So, this term, that is the energy stored in the arrangement by bringing the current from 0 to capital I. So, that leads to equals to half mu H square S V C, where H is the magnetic field intensity in the core and V is the volume of the core. So, therefore, per volume the corresponding energy stored per volume becomes equals to half mu H square, and this mu H equals to B. So, that becomes equals to half into B H, or you can say also that in terms of B square upon 2 mu. So, we say that energy per cubic meter in this arrangement, magnetic core arrangement, will be equals to B square upon 2 mu, or you can say half B H or half mu H square. So, that is about the self inductance and the energy associated. Next, we will go for the mutual inductance. The term mutual is there. Now, let us consider two coils here, coil 1 and coil 2, and they have self inductances of L 1 and L 2, N 1 square by S 1 and N 2 square by S 2, like that. So, let us say the coil 1 has a current of this and coil 2 has a current of 0 current, coil 2 has a current of 0 current and coil 1 has the inductor current I 1 t, and this establishes a flux of phi 1 through that coil, which phi 1 links to the cell and phi 1 2 links to the other coil. So, total flux produced by the coil is phi 1, coil 1, that is having inductance L 1, and out of which phi 1 as you see here, phi 1 on this part only links the coil itself, it does not link to the other coil, and phi 1 2 links the other coil. So, 1 here means cell, only to cell, and phi 1 2 is generated from 1 and linked to 2, and the combined is phi 1 plus phi 1 2 is phi 1, which is produced by 1. Now, see here the two coils are physically separated, but magnetically coupled by a flux of phi 1 2 produced by 1 and linking to the 2. Now, let us analyze the coil 1. In coil 1, the voltage V 1 as marked here equals to N d phi by dt. The induced EMF in coil 1 is N d phi by dt. So, N 1 d phi 1 by dt. So, now this we can write down also like earlier N 1 d phi by d I 1 into d I 1 by dt, and that becomes equals to L 1 d I 1 by dt. So, this is about the self inductance of the coil L 1. Now, if you see this coil 2 where the corresponding flux linkage is phi 1 2 contributed from first coil. So, V 2 equals to N 2 d phi 1 by dt, d phi 1 2 by dt, because coil 2 has been number of turns 2 and a flux available to it is phi 1 2. So, N phi 1 2 is the flux linking. The derivative of that upon dt is the corresponding voltage induced in 2. Note the second coil has no current. So, therefore, V 2 in the similar way equals to N 2 d phi 1 by d phi 1 2 by d I 1 into d I 1 by dt, and that becomes equals to, we can refer it as M 1 2 d I 1 by dt, where M 2 1 is N 2 d phi 1 2 by d I 1. So, what to mean here that like the self inductance case, if we formulate the corresponding N 2 d phi 1 2 by dt like this, where the corresponding flux which is produced is due to the by the I 1, current change in first coil results in flux change in the second coil. So, we formulate the corresponding relations for the V 2 voltage in coil 2 to be M 2 1 t I upon dt, then the corresponding M 2 1 is N 2 d phi 1 2 by d I 1. Note that here N 2 is the number of turns of the coil 2, phi 1 2 is the flux linking to 2 generated from 1 2 and current in 1 d I 1. So, change of current in 1 results in change in flux in 2, and that results in an induced EMF in 2, and that we call the mutual inductance part M 1 M 2 1. So, similar to this first expression for the self one, we got an expression for the mutual one in terms of M 2 1 d I 1 by dt. This M 2 1 is called also the open circuit mutual voltage. Mutual means because it is the second coil which we are talking about the corresponding voltage induced, and this V 2 equals to M 2 1 d I 1 by dt. Note that M 2 1 d I 1 by dt, change of current in 1 is resulting in voltage develop in 2. So, that is why I talk about M 2 1. So, M 2 1 is known as the mutual inductance of the coil 2 with respect to phi 1, which is resulting from the coil 1 in this case. Similarly, if we inject a current in second coil and I 1 remaining same, so we see that the phi 2, which is the flux developed in second coil, part of this is only linking to the first coil, and part is only linking to the self. So, phi 2 2 is the self is in of its own, you can say this path, and phi 2 1 is linking to the other coil, coil number 1, similar to what we discussed in case of the coil 1 organization and coil 2 open circuited. So, the total flux produced in this coil 2 is phi 2, and then phi 2 1 links to both the coils, and phi 2 2 is linking only to the coil itself. So, here in this case, similar to the earlier analysis, the V 2 equals to N 2 d phi 2 by dt, and that equals to L 2 d I 2 by dt. So, this is about the cell, and the in coil 1 we have V 1 voltage induced now due to the flux linking from second coil. So, that becomes equals to N 1 phi to 1, phi to 1 here refers to that linking to one source from 2 upon dt. So, that becomes equals to N 1 d phi 2 1 upon d I 2 into d I 2 by dt M 1 to d I 2 by dt. Note that the corresponding we are taking I 2 here, because I 2 is responsible for the voltage induced in the coil number 1. So, that results in the corresponding M 1 2 becomes equals to N 1 d phi 2 1 upon d I 2 N 1 first coil where we are observing the voltage induced, d phi 2 1 the linked flux, and the region behind is the I 2. So, that becomes M 1 2 becomes equals to N 1 d phi 2 1 upon d I 2. Now, you can compare the corresponding cell versus this. So, here the corresponding mutually the wherever you are observing the corresponding induced EMF corresponding to that number of turns, the linked flux to the both the coils and the corresponding source of the current, that is the first coil. So, therefore, the corresponding voltage V 1 develop in the second one we call the open circuit mutual voltage, that happens to be M 1 to d I 2 by dt. So, in both the cases we say that from symmetry point of view the M 1 2 becomes equals to M 2 1. So, coil 1 flux linking to coil 2 or coil 2 flux linking to coil 1 in general. From symmetry point of view this M 1 2 becomes equals to M 2 1. From this mutual inductance we define a term also called coefficient of coupling or coupling coefficient. So, let us see what it is. Let us consider a circuit like this with N 1 turns in the first coil and N 2 turns in the second coil, and they are around a core. So, the inductance of the first coil is L 1 equals to N 1 square upon S, S is the corresponding reluctance of the core. So, for the second one same reluctance, so that becomes equals to N 2 square upon S. So, S equals to N 1 I 1 upon phi 1. So, when we only energize the coil 1 with I 1 current and at that time I 2 equals to 0. So, at that time the corresponding S becomes equals to N 1 I 1 upon phi 1, where phi 1 is the corresponding flux in the core at that time. Similarly, S equals to whenever we energize the corresponding circuit with only I 2 and in that case I 1 equals to 0, the corresponding flux will be phi 2. So, that becomes equals to S equals to N 2 I 2 upon phi 2, S phi equals to N I MMF. So, from that relation we are getting. So, but in this case we are energizing one coil and keeping the other coil current to be 0. So, this becomes equals to gives us that the like we talk about the average value of inductance M equals to N 2 phi 1 upon I 1, the region behind here. So, when we are energizing only with I 1, so this establishes a flux phi 1 which links to the second coil also. So, therefore, phi 1 in the second coil has a number of terms N 2 and then the corresponding current of the first one is I 1 N 2 phi 1 by I 1 for this arrangement. Now, if you multiply N 1 in the both in numerator denominators, then the relation becomes N 1 N 2 phi 1 upon N 1 I 1. So, this becomes equals to N 1 N 2 upon S as we have defined the S above. So, this results in this case N 1 N 2 upon S. So, if you say that this case N 1 root over S into N 2 root over S. So, that results in this to be equals to N 1 square by S is L 1 and N 2 square upon S is L 2. So, this results in N 1 N 2 upon S equals to root over L 1 L 2. So, what we say here that with the consideration of the no leakage flux in the circuit, the corresponding mutual inductance of this arrangement becomes root over of L 1 L 2. But now, we say that the flux produced by coil 1 may be linking in this path also, which does not link to the coil 2, because the coil 2 links the flux links which goes to the core. So, that is about the leakage flux. So, in this kind of environment the M can be expressed in terms of in ideal non-ideal case M equals to k root over L 1 L 2 and k can be from 0 to 1, varying from 0 to 1 depending on the leakage perspective or the the linking flux from 1 to 2 or 2 to 1, vice versa. The k here is called the coupling coefficient. When k equals to 1, m equals to root over L 1 L 2. So, perfect this is no leakage flux. So, it is a perfect case, ideal case. So, k is called the measure of magnetic coupling between the two coils. If it is closer to 1, the coupling is excellent. If it is closer to 0, the coupling is very poor. So, from this above, we can say that the M, the mutual inductance between coil 1 and coil 2 in this arrangement equals to is varies from 0 to less than equals to root over L 1 L 2. When k is 1, no leakage flux, M becomes equals to root over L 1 L 2. There is another way of saying the coupling coefficient is a fraction of the total flux. So, k becomes equals to phi 1 2 by phi 1. Phi 1 is the flux produced by coil 1 for I 1 current, and phi 1 to the corresponding flux linking to 2 generated from 1. And so, therefore, this becomes equals to, as we have already defined earlier, phi 1 2 upon phi 1 1 plus phi 1 2, where phi 1 1 is the corresponding flux linking only to the self. Similarly, k can be expressed also phi 2 1 upon phi 2, when I 2 current is injected, it produces phi 2, and then only phi 2 1 links to the coil 1, and then this ratio can be phi 2 1 plus phi 2 1 plus phi 2 2, where phi 2 2 is the corresponding flux only linking to coil 2 with current I 2 without current in the first coil. Let us take an example now. So, there are two coils here with N 1 and N 2 turns, and they are connected in series like this. So, in both the cases the corresponding current directions can be like this. So, the flux is in a direction, in same direction the flux happens to be there contributed by both the circuits. So, an ironic of cross sectional area 800 mm square of mean radius of 170 millimeter has two windings connected in series, one having 500 turns and the other having 700 turns. If the relative permeability is 1200, mu r is 1200, calculate the self inductance of each coil and the mutual inductance assuming there is no flux leakage. So, k becomes equals to 1 in this case. So, as here the reluctance becomes equals to L upon mu r mu naught mu r into A. So, that we got the from this substituting the different value. So, L 1 becomes equals to n square upon S. So, we got the L 1 to be 0.28 Henry and L 2 to be n 2 square upon S, we got to be 0.552 Henry, n is larger in this case, and then m equals to k root over L 1 L 2 and k is 1 in this case. So, we got the corresponding mutual inductance to be 0.395 Henry. Now, convention called dot convention widely used in the coupled circuits. Now, let us say two coils are adjacent to each other as shown here. So, coil 1 is energized with a current injection of I 1. Now, these coils are inside a box. So, depending upon the orientation of the second coil with respect to the first coil, the corresponding voltage which will be induced in the second coil, the induced EMF in the second coil will be M, we say that M d I 1 by dt, M d I 1 by dt. Now, this M d I 1 by dt, whether this will give you a plus or this will give you a minus in terms of the polarity at one instant of time is not known to one, and that depends upon the orientation of this coil. So, because this is inside, so therefore, the manufacturer or the producer will provide information on that how the what is the corresponding polarity for this kind of arrangement, and that is given by the called the dot convention. So, dots are provided outside the corresponding box, so that you can know the corresponding polarity which will be developed due to the mutual inductance of the circuit. So, the M becomes positive in this case when the dot terminals becomes like this. If to the dotted terminals the corresponding current is entering in the first coil, then the dotted terminal in the other one that becomes positive and this becomes negative. So, the corresponding V 2 becomes equals to M d I by dt. Note that this positive and this negative are the measurement side at the terminals. So, with respect to this the corresponding measurements V 2 becomes equals to M d I by dt is positive. However, if it happens to be the other way, if to the dotted terminal the current is entering in the first terminal, then the dotted at the dotted terminal, then if the measurement is this here is plus and minus, then the corresponding V 2 happens to be equals to minus M d I by dt. It means that the dotted terminal will be positive at any instant of time if the corresponding current is entering to a dotted terminal in the first coil. This can be seen in another way also using the Lenz's law. So, let us say in the first coil, if the corresponding current is entering current is entering I A, and the corresponding current the corresponding voltage induced as per the earlier discussion, we saw that the corresponding voltage which will be induced is this. So, this M d I A by d t. So, in that case the corresponding, if you connect any impedance also, the corresponding current will flow like this. So, this current flowing will result in the corresponding as per the Lenz's law, this current will result in to a flux produced by the coil 2, which will oppose the corresponding cause. The cause is nothing but the first current flux produced by the first current. So, therefore, what will happen that in that case, if the corresponding current flows like this, the corresponding flux will be opposed in the main one, and then the flux will be reducing. So, that means that this is case of a minus M case, if the corresponding current flows like this. However, to the dotted terminal, if the current is entering the other one, then the corresponding M becomes positive in that case. So, this is from Lenz's law. So, we see that in general, to the dotted terminal, if the currents are entering, the M is positive, and if the otherwise the M becomes negative in negative. So, that the convention, dot convention is be used in coupled circuit, because the orientation inside the of the coil is not known outside the box. So, in this we have an example on mutual inductance. So, the circuit is shown here. So, we have L 1 and L 2 two inductances, self inductances, and current I 1 is entering to the dotted terminal, and current I 2 is leaving the dotted terminal in the second coil. So, the question asked is determine V 1 t if I 2 equals to 2 sin 40 t ampere and I 1 equals to 0. So, there is no current flowing in the first coil, only I 2 is flowing in the second coil. So, with I 2 current flowing, what will be the corresponding voltage induced in the first coil? That is our question. Now, you see here in these two arrangements, I 2 is leaving to the second coil. So, therefore, the corresponding voltage will be developed here in the first coil will be also in the undotted terminals. These undotted terminals, this side will be positive, this side will be negative, but the measurement process is marked as positive and negative here. So, this leads to the corresponding M to be negative. So, therefore, the V 1 2 becomes equals to minus M d I 2 by dt, minus M d I 2 by dt. Minus M, we are talking about the observing the first coil, minus M because of the dot convention, and current the energized coil 2 in this case. So, the open circuit voltage in 2, this V 1 2 becomes equals to d I 2 by dt. So, M is here in this case 2 Henry. So, we got this M to be 2, and d I 2, the derivative of this I 2 t, that becomes equals to 240 into cos 40 t. So, that gives us the corresponding value to be minus 160 cos 40 t. So, this will be the voltage developed in the first coil for this case, and why you got this minus? Because of the dot convention, the corresponding voltage developed in the first coil when the corresponding second coil is being energized with a current like this. So, example with M in the circuit. So, the corresponding M becomes equals to here that there are two coils connected, coil A and coil B, and then the dotteds are put like this. So, the current I flows here and flows here like this. So, if you see here the corresponding current direction will be like this and this. So, if you see that the corresponding flux both by produce will be the same direction. So, therefore, the corresponding flux becomes additive. So, the M will be in this case will be positive. So, then current here is entering also dot and current here also entering dot. So, that means that the M is positive in our case. So, if you see this, then the total EMF induced across the two terminals of the arrangement, that becomes equals to L A d I upon d t, first coil self inductance, L B d I upon d t, second coil self inductance related voltage, and then the first coil M d I by d t, mutual inductance related voltage, and the corresponding mutual inductance voltage in the second coil m di by dt. So, this results in the common term di by dt throughout, because same current is flowing L A plus L B plus 2 m. So, the equivalent inductance of the arrangement becomes equals to L A plus L B plus 2 m. So, that results in the corresponding calculation for the inductance of the arrangement becomes this. So, with the dot convention being used, we can find out the corresponding inductance of the circuit as in the seen in the circuit. Another example, with the L1, L2 and L3 connected in series, find the equivalent inductance of the circuit. So, the values of L1, L2, L3 self inductances are given, and then second case the corresponding M12, this M12 equals to 5 Henry, M23 equals to 3 Henry, and then M13 equals to 1 Henry. So, values of these corresponding the mutual inductance M12, M23 and M13 are also given to us. Now, if you see here the dots here, the dots here are like this. So, same current is flowing here series path, let us say I. So, then in the first coil the current is entering to the dotted terminal, second coil also the current is entering. So, that means that M12 will be positive, right, and then in first coil the current is entering, and to the third coil the current is leaving. So, M13 will be negative. Second coil current is entering to the dotted terminal, and third coil the current is leaving to the dotted terminal. So, M23 will be also negative. So, the L equivalent becomes in this case will be L1 for first coil, it has a 2 mutual inductances with 2 and 3. So, L1 plus M2 plus M12 minus M13, second coil L2, it has 2 inductances mutual inductance with L1 and with L3. So, with 2 3 it is negative already defined, and 2 with 1 2 we can say that it is positive. So, minus M23 plus M12, third coil has also 2 inductances mutual. So, L3 of itself and its mutual is minus M23 and minus M13. So, with the other 2 coils. So, this results in the corresponding expressions to be like this, and if we substitute all the values, the corresponding L equivalent comes out to be 39 Henry in this case. So, we have an example on series connections of inductances. So, this example is on 2 identical coils with terminals T1 and T2, T1 T2 is one coil and T3 T4 is another coil, are connected as shown. The inductance as measured for the 2 different connections, connection 1 and connection 2. So, the inductance measured for the 2 connections are as follows. When T2 is connected to T3, T2 is connected to T3, and the inductance measured between T1 and T4 here and here, then we are getting 4 Henry. We are getting 4 Henry. When T2 is connected to T4, not T3, T2 is connected to T4, this is the connection. Then the inductance measured between T1 and T4, T1 and T3, this and this. So, in this second one, then the corresponding inductance becomes 1 Henry. So, in one case we are getting 4 Henry, the other case we are getting 1 Henry. So, determine the self inductance of each coil, the mutual inductance between the coils and the coefficient of coupling. Self inductance, mutual inductance and the coefficient of coupling K. These are to be found out from these observations. So, in first case, first connection, we say that we are getting higher inductance for the combinations, and in second case we got the lower one. So, therefore, we say that the first case the corresponding combination will be, because inductance they are identical coils. So, inductance each inductance let us say L and L. So, the corresponding first case the connection will lead to L plus 2 m, this must be 4 Henry. Second case similarly lower one L plus L minus 2 m, this must be 1 Henry. So, these are the 2 equations we got. So, we say that if we go by this 2 L plus 2 m equals to 4 H. So, this implies L plus m equals to 2 and in this case L minus m equals to 0.5. So, this leads to L equals to 1.25 Henry and then m equals to 0.75 Henry, simple straightforward from this. But then the k, the coefficient of coupling k, that is as formula is m root over of L 1 L 2 or here both are L and L root over of L L L square. So, that becomes equals to L. So, then this becomes equals to m upon L, m upon L. So, that is the corresponding thing. So, we substitute the value of m and L. So, this becomes equals to in this case equals to 0.75 upon the 1.25. This is about coefficient of coupling for this. So, we see here. So, each as I said L 1 L plus 2 m equals to 4, L plus m equals to 2 and then L minus m equals to 0.5. So, L comes out to be 1.25 Henry, m comes out to be 0.75 Henry and k equals to m root over of L 1 L 2, that comes out to be equals to 0.6 value. So, it is the coefficient of coupling 0.6 means it is 60% coefficient of coupling happens to be there between coil 1 and 2 in these two arrangements. So, the two coils are coupled with in that environment. Energy in case of the mutual inductance, like self inductance we found the half Li square. So, let us say consider two coils are there adjacent to each other on a core and then we have a IV current flowing here. So, IV current in coil B, if IV current is supplied to A now. So, now you supply you can say that IV current to A now. So, EMF induced in B, for the EMF induced in B, additional EMF induced in B due to the current injection in A will be m di upon dt, because they have mutual m. So, the additional energy absorbed by B due to this current injection in A will be equals to E into E developed here into the corresponding injected current. So, that becomes equals to E, that is I B into the corresponding induced EMF developed into time dt, interval time is nothing but the energy associated in a time interval of dt. So, that becomes equals to I B m into d I. Now, the total energy, like we all know that half Li square for the first self inductance, first half L V square as I B square equals to for the second inductance, and the plus minus means depending upon the m, that depends upon the dot signs or the corresponding flux are additive or subtractive. So, that becomes equals to the integral of this value for this from 0 to IA increment current for this coil I B flowing in the second coil. So, this becomes 0 to IA IBM DI this value. So, that becomes equals to half LAI square half LBI square plus minus m into IIB. So, we see that the energy associated with this arrangement, complete arrangement of the coil A and coil B becomes half LAIA square plus half LBIB square plus minus m IIB plus or minus m depends upon the dot conventions, flux additive or subtractive, and this becomes equals to IIB. So, we can summarize that here half m IIB for first coil and half m IBIB for the second coil contribution for the mutual part. So, the total energy in a coupled circuit also can be found out like this. So, in general remarks, in this case we discuss about inductance both self of its own and the mutual, the contributed EMF developed in the second coil and that results in the mutual inductance definition. So, these self inductance and mutual inductance they have their own applications also, like in power systems we see inductors are being connected to support reactive power generate support in the high voltage systems. Inductors are also connected in different electric circuits to control the current, and for that perspective even they are model, because like in resistance in a circuit of its the property of the conductor. Similarly, any current flowing in a conductor results in an inductance. So, in modeling also we need to consider the inductances also. If coils are adjacent to each other, we need to consider the mutual inductance also. Dot convention is used because as I said we do not know the orientation of the coils inside a box. So, dot helps us in whether the corresponding M value will be positive or the voltage developed will be positive or negative with respect to the terminals, and also is studied on stored and energy stored in inductors including the mutual inductance. Thank you.